Hello everyone, my name is Naina and I'm from the Buddhi Academy. So today we'll continue with the chapter that is classification of elements and periodicity in their properties. So in our last video we have seen about the electronic configurations and how they are related to periodic table. Like electronic configuration along how it affects the periods as well as the groups. Then we have also seen about the S block, D block, F block and P block elements, how they are classified and what are the characteristics of each blocks. Then we have also seen about metals, non-metals and metalloids. Now in today's video we will see the periodic trends and properties of elements. Now what are the trends that are followed by the periodic table? Okay, now there are many observable patterns in the physical and chemical properties of elements as we descend in group or move across a period in the periodic table. So all these elements, as I told you, starting they were arranged in the form. The elements in a periodic table, they are arranged on the basis of their increasing atomic masses, right? But later Mendeleev, what he proved was, if we arrange them in according to their atomic weight, okay, it doesn't show a sense, right? More than what he considered to fill the periodic table with elements observing their properties, physical and chemical properties. The elements which showed similar physical and chemical properties, he started to place them in one group or one period. Okay, so to know that there are many physical and chemical properties of elements, right? And each of them, they either increase or decrease in the group, okay, or across the period. Okay, sorry. So either they will increase or decrease in the group from top to bottom, or it will increase or decrease from left to right in the period. For example, within a period, chemical reactivity tends to be high in group 1 and lower in elements towards the middle of the table and increases to a maximum in group 17, that is non-metals. Okay, so when you see in a period, okay, in a period is from a horizontal line from left to right. So in a period, if we want to check the chemical reactivity, okay, it is high at the group 1 elements. Okay, group 1 elements, the period is the chemical reactivity is high. As we go from group 1 to the middle group, okay, that is from 3 to 12, okay, 3 to 12, in the middle you can see the reactivity in so the lower, okay, the chemical reactivity is high in group 1, but as we go to lower elements in towards the middle of the table and increases to a maximum at the group 17. So from group 1 it increases and it decreases in group 3 to 12, that is the middle group. Again it will increase when it reaches the group 17. Okay, so you can see there is a increase, decrease, increase, right? Something like this. So likewise, within a group of representative metals, say alkali metals, reactivity increases on moving down the group. So in a group, if we take, this is a group, in a group if we take, for example, alkali metals, okay, that is the group 1 elements, okay, alkali metals, as we go down the group, okay, their reactivity increases on moving down the group. Whereas within a group of non-metals, okay, within a group of non-metals, for example group 17, that is the halogens, okay, reactivity decreases as you go down the group. So here your reactivity increases, here your reactivity decreases as we go down the group. Both are down the group, but one is increasing, other is decreasing. So there is a trend which is followed here, right? But why do the properties of elements follow this trends? Why do they follow these trends? Why there is some increasing ones, some decreasing ones? As you go, there is increase, decrease, increase, decrease. Why do they follow this? Okay, so this is basically, to answer these questions, we must look into the theories of the atomic structure and properties of the atom. Okay, to understand why there is this increase, decrease, and all these things we have to understand the structure and property of the atoms. Now in this section we shall discuss the periodic trends in certain physical and chemical properties and try to explain them in terms of number of electrons and energy levels. So here we will see some trends in the periodic table, on what basis those trends are set and what are the ones which affect these trends, either the number of electrons or the energy level. Okay, now trends in physical properties. First we will start with physical properties. Now there are trends in physical properties. There are numerous physical properties of elements such as melting point, boiling point, heating of fusion, vaporization, and vaporization, energy of atomization, etc. So what are the physical properties? Some basic and common physical properties are melting and boiling point, heat of fusion and vaporization, how they fuse, how they vaporize, energy of atomization, okay, etc. Now which show periodic variations. However, we shall discuss the periodic trends with respect to atomic and ionic radii, ionization enthalpy, energy gain enthalpy and electronegativity. So here we will be only discussing, since there are various properties on the basis of which this physical trend is there. For y'all, as of now we have atomic and ionic radii, ionization enthalpy, electron gain enthalpy and electronegativity. These are the things that we will be learning in this part. Now first one is the atomic radius. Now you can very well imagine that finding the size of an atom is a lot more complicated than measuring the radius of a ball. Yes or no? Ball, you can hold it in your hand and measure the radius. What about atoms? They are so indivisible. Indivisible metals are there, no? So those are so small, you can't even see them with your naked eyes. How you will take their radius, right? Do you know why? Firstly, because the size of an atom, yes or no, size of an atom is very small. You can't even see it using your naked eyes. Secondly, since the electron cloud surrounding the atom does not have a sharp boundary. Firstly, because they are very small. Secondly, there is an electron cloud around the atom. Okay, and this electron cloud doesn't have a sharp boundary. So the determination of the atomic size cannot be precise. So you cannot determine the size precisely or exact size, that an atom is this much nanometers. You can't predict that because of their electron cloud around the atoms, around the atom. If this is an atom, there is an electron cloud, and that electron cloud doesn't have a sharp boundary. It doesn't have this circular thing. Okay, it is distorted. It doesn't have a sharp boundary, and because of this you cannot predict or determine the atomic size of the atom. Now in other words, there is no practical way by which the size of an individual atom can be measured. So there is, even practically also, there is, theoretically also we can't do anything, practically also there is no way you can find a size of an individual atom, a single atom. Okay, now however, an estimate of the atomic size can be made by knowing the distance between the atoms in the combined state. Okay, so how you will find the atomic size? You can find the atomic size when they are in a combined state. Okay, when that atom is combined to another atom of same or different kind. Okay, once they are combined, you can estimate. Okay, it's not like you are telling it this is the size of the atom. It's just an estimation. Okay, this can be the size of the atom. So you can estimate the atomic size by knowing the distance. Okay, if when they are combined, by knowing the distance between the two atoms, you can predict its, or you can estimate its atomic size. Okay, one practical approach to estimate the size of an atom of a non-metallic element is to measure the distance between two atoms when they are bound together by a single bond in a covalent molecule, and from this value the covalent radius of the element can be calculated. Now how we will do that? So this is a theory, right? If the atom is combined, by measuring the distance you can estimate the atomic size. Now, when you practically approach it, Okay, when you practically try to do that, to estimate the size of an atom. Okay, now here they have taken non-metallic elements. Okay, two non-metallic elements. They have measured the distance between them when both of them are bound together by single bond. Only one bond is involved. Okay, when single bond, and in a covalent molecule. So single bonds, you know that covalent molecules. Now from this value you get a covalent radius of the element which can be calculated. Okay, now for example, the bond distance in chlorine molecules. Okay, bond distance between chlorine molecule. Chlorine is a non-metal. Okay, now chlorine molecule, that is Cl2, that is 2Cl, Cl and Cl. So there is a bond between, single bond between both the Cl molecules. Now this is 198 picometers. PM is picometers. Okay, and half distance is 99 pm. If 198, if you divide it by half, it is 99 pm. Okay, so is taken as the atomic radius of chlorine. So 198 is the entire distance, is the complete distance. When you divide it by 2, because it is two elements that are attached, so when you divide it by 2 you get 99 pm, and this 99 pm is considered to be the radius of one chlorine atom. Okay, now for metals we define the term metallic radius. Okay, covalent radius is for non-metallic things. Okay, for metals we have metallic radius, which is taken as half the internuclear distance separating the metals cores in the metallic crystal. So it is the internuclear distance. It is a distance between the nucleus which separates the metal's core from the metallic crystals. Okay, which separates the metal core in the metallic crystals. For example, the distance between two adjacent copper atoms in a solid copper. Okay, if you have two copper, okay, the distance between these two copper in a solid is 256 picometer. Hence the metallic radius of copper is assigned a value of 128 picometers. For simplicity, in this book we use the term atomic radius. Okay, actually it is covalent radius or metallic radius. For simplicity we use it as atomic radius. Again same thing, this distance was measured and it was divided by 2, and that answer is considered to be the value for or radius of the one copper atom. For simplicity we are considering it to be atomic radius to refer both covalent and metallic radius depending on whether the element is non-metal or a metal. Okay, in general we use a atomic radius term, but depending upon whether it is a metal or non-metal, the term covalent or metallic radius is taken. Now atomic radii can be measured by X-ray or other spectroscopic method. Now how you will determine atomic radii? You can determine atomic radii by X-ray or spectroscopic method. Okay, now the atomic radii of a few elements are listed in table 3.6. So here some of the atomic radii are mentioned. Now two trends are obvious. Okay, there are two trends which are followed. Now we can explain these trends in terms of nuclear charge and energy level. Okay, two trends explained in terms of nuclear charge and energy level. Now the atomic size generally decreases across a period as illustrated in figure 3.4. So the atomic radius decreases. Okay, atomic size, it generally decreases across the period as illustrated for elements of second period. Okay, for elements of second period, okay, that is from lithium. Okay, from lithium second period, you can see the atomic size or atomic radius, it decreases. You can see this decrease, right? It decreases as we go along the period, as we go across the period from lithium to beryllium, boron, carbon, nitrogen, oxygen, fluorine. Okay, as we go from lithium to fluorine across the period. Okay, along the period when we go, the atomic size, it decreases. Okay, now It is because within the period the outer electrons are in the same valence shell. Okay, and the effective nuclear charge increases as the atomic number increases, resulting in the increased attraction of electrons to the nucleus. Now why there is a decrease in atomic size? Along the period, okay, along the period as you go, you are not adding extra shells. Second period will have 2s and 2p electrons, right? So the energy level is 2 only, and you are adding no extra orbits till 2p orbit is present in the second period, and you are adding electrons to the same orbital, right? The electrons are being added to same orbital. For example, from lithium, beryllium. Okay, here 2s orbital is completely filled. From boron till fluorine, you will start filling the 2p orbital, right? 2p1, 2p2, 2p3 and so on till you reach 2p6, right? So here what is happening? You are adding electrons to the same shell, to the same orbital. You are not adding extra orbital. You are adding electrons to the same orbital. So when the electrons are added to the same orbital, okay, the valence shell is same, that is 2p. Valence shell is 2p only, and the effective nuclear charge increases. So since you are adding more and more electrons, the charge in them increases. Okay, the nuclear charge increases. Now as the atomic number increases, resulting in the attraction of electrons to the nucleus. So as the nuclear charge increases, as you go on adding electrons, it will be attracted towards the nucleus of the atom. You know, atom has a nucleus and surrounded it are the electrons. So this is 2p orbital if you consider. Okay, you are adding more and more electrons to this 2p orbital. So the nucleus will attract all those electrons towards itself. Okay, so the attraction it increases the attraction of electron towards the nucleus. So since the attraction towards the nucleus increases, it will shrink. So the atomic radius, it decreases as we go from the left to right of the period. Okay, now within a family or vertical column of the periodic table, the atomic radius increases regularly with atomic number. Okay, so as we go down the group, okay, as we go down the group, the atomic radius increases. Why? Because new shells are start adding up. Okay, here only what happens, only same shells it has, we are adding electrons to the same shell. Here we are adding electrons to different shells, because as we go down we are increasing the periods, right? So first period has 1s, second period has 2s, third period has 3s. So as we go down, we are increasing the energy levels, and we are increasing the number of orbitals that are being added. Now for alkali metals and halogens, as we descend the groups, the principal quantum number increases and the valence electrons are further from the nucleus. So this happens because of the inner energy levels are filled with electrons, which serves to shield the outer electrons from the pull of nucleus. So as we go down the group, okay, why this happens is basically because the valence electrons, okay, are farther from the nucleus, are far away from the nucleus, because you are being adding new shells. So as you go on adding new shells, it will go away and away from the nucleus, right? Another point is that the orbitals which are close to the nucleus, okay, those orbitals will have electrons already filled in them, and those electrons will shield the outermost electrons from the nucleus. Okay, they will act as a shield because they are always present in front of the nucleus, or in between of the nucleus and the outermost electron, right? If this is the nucleus, these are the shells, this is the outermost shell, and here I have one electron, but all these three shells, they also have electrons in them. These electrons will shield the outermost electrons from the nucleus, so it won't be pulled towards the nucleus. Hence the radius is hence the size is bigger than the elements in a period. Okay, in a period in a period it decreases, but as we go down the group it increases. Okay. Now consequently the size of atom increases as reflected in the atomic radii. Now note that atomic radii of noble gases are not considered here. So atomic radii of noble gases are not considered here because being a monoatomic, their non-bonded radii values are very large. In fact, radii of noble gases should be compared not with the covalent radii but with the van der Waals radii of other elements. So here noble gases, they doesn't have much reactivity, and if they react also the value is very large. Okay, so you can't compare them with covalent radii, but you can compare them with van der Waals radii. Okay, so radius, atomic radius we can't predict. Now ionic radii. Now, the removal of an electron from an atom results in the formation of a cation, whereas gain of electrons leads to an anion. So ionic radii you can get a cation or an anion. So what is a cation? When we remove an electron, okay, when we remove an electron from an atom, you get a cation with the positive sign, whereas when you gain an electron from another atom, you will get an anion with a negative sign. Now the ionic radii can be estimated by measuring the distance between cations and anions in ionic crystals. Okay, so the ionic radii you can estimate it by measuring the distance between cations and anions in an ionic crystal. So a simple example is NaCl. Okay, here Na is positive, Cl is negative. So this is an ionic crystal. So if we measure the distance of anion and cation in this ionic crystal, you can get ionic radii. Now in general, ionic radii of element exhibits the same trend as the atomic radii. So here also the trend remains same compared to atomic radii. Okay, atomic radii along the period it decreases, along the group it increases. So same thing is there for ionic radii. A cation is smaller than its parent atom because it has fewer electrons while its nuclear charge remains the same. So a cation is smaller. Okay, so if sodium we take, sodium is a cation, Na plus is a cation. So Na plus cation is smaller than the Na molecule. Na molecule with complete electrons. Okay, without removing an electron, a complete Na molecule. Compared to this complete Na molecule, Na plus molecule is smaller. Okay, because of its removed electrons. Okay, because there is fewer electrons. The number of electron is less because we are removing one electron, right? So because of its fewer electrons, while one thing remains same, that is their nuclear charge, whether it is completely filled or whether electron is removed. Okay, both the cases their nuclear charge remains the same. Okay, now the size of an anion will be larger than that of the parent atom because there is an addition of one or more electrons that will result in increased repulsion among the electrons and decrease the effective nuclear charge. So compared to cations, what will happen to anion? Anions will be larger because anions will take in electrons. Once they take in electrons from their original size, they will increase. Why? Since they are taking one electron in, there will be repulsion among the electrons because there was no electron. Now you are having one electron in that. So there will be repulsion between the electrons that will increase the size, and there will be decrease in their effective nuclear charge. Okay, the nuclear charge will be decreasing because of repulsion. The size will increase, so the electrons will go away from the nuclear. So the nuclear charge will be decreasing. Now for example, the best example for an ionic this thing is fluorine. Fluorine only requires one electrons to complete its electronic configuration. So when it takes one electrons, it will become 136 picometers, whereas the atomic radius of fluorine is 64 picometers. So atomic radius of fluorine is only 64 picometers, but when it takes one electron and becomes F minus, the radii changes to 136 picometers. On the other hand, the atomic radius of sodium, I told you sodium ka atomic radius is 186 picometer compared to the ionic radius of 95 picometer. So sodium का radius is 186 picometers, but when it loses one electron, okay, when it loses one electron, the radius of sodium becomes 95 picometers. Okay, now when we find some atoms and ions which contain the small number of electrons, we call them isoelectronic species. So when some atoms, okay, or ions which contain the same number of electrons, okay, when an atom or ion, when they contain same number of electrons, we call them as isoelectronic species. For example, O2 minus, F minus, Na plus and Mg2 plus. They have same number of electrons, that is 10. Okay, they all have same number of electrons in their shells, that is 10 electrons. These are called as isoelectronic species. Now their radii would be different because of their different nuclear charges. Even though they are having same number of electrons in them, but because of their charges, their radius will be different. Okay, because O is 2 minus, whereas Mg is 2 plus. This is plus and this is minus. Plus means the size of Mg will decrease. O2 minus means the size of oxygen will increase. So because even though they have same number of electrons, but because of these charges, okay, their atomic radii or their radii will be different. Okay. Now the cation with greater positive charge will have a smaller radius because of the great attraction of electrons to the nucleus. Okay, so cations will have smaller radius. Why they will have smaller radius? That smaller radius will be because of the attraction of electrons to the nucleus. And anions, they will have greater negative charge and have a larger radius. Okay, anions with greater negative charge will have larger radius. In this case, the net repulsion of electron will outweigh the nuclear charge and ions will expand in size. Now, why anions will have larger radius is because they are taking in electrons, so there will be repulsion between the electrons. So the electrons will push each other far away from the nucleus, so the nuclear charge will decrease and the ions will expand. Okay, so in this video we have seen about the atomic and ionic radii, their trend along the period, along the group, and why they show this trend. Okay, so these are some properties. In this we have seen atomic and ionic radii. Remaining are the ionization enthalpy, electron gain enthalpy and electronegativity that we will do in our next video. So thank you for watching my video. Please do like, share and subscribe to our channel.